Welcome everybody to this webinar today on finite element analysis. It is moving forward from the previous webinar on frame analysis, hints and tricks. This is the advanced finite element area of that. So I'm just going to go through and look at our product range. First, just a quick talk. We have the big building design suite, and yes, there's finite elements in it. We have the small power pad, and although it doesn't show up, there is a single FEA surface facility inside that. We also have all the standalone programs, but if we look at the full product range, we'll see these three, and then we'll see all the different modules. So the basic would be a frame analysis engine and the finite elements. So those two together will get you what we're going to be doing today. Be that with the building design suite, be that with the power pad, or just those two modules on their own. So three different ways to think about the finite elements. And let's have a quick look at the finite elements. It does pretty things. It handles surfaces very efficiently. So what I'm going to do first of all is I'm going to walk through how to create a finite element surface. And I'm just going to minimize Chrome. And we're going to come back out of this. We'll come back to this structure in a wee while. I'm going to go to something a lot more basic. Well, I say basic, so I don't know why. And what I'm looking at is I'm looking for this simple structure. There are no FE surfaces, there's just an area loading on the roof. I'm just going to take that off for you. So in 3D, you've got concrete columns, you've got nothing attaching some of those, so they're just sitting in space. You have this steel superstructure sitting in space, and obviously a balcony all the way around it. And we're going to make that first floor into an FE slab. And that is very, very simple. Just go back to wireframe, and just to make my life easier, I'll just turn off all the coloring and maybe get rid of the dots. So create a slab wall ramp, an FE surface. And we can make any 4 members, 5 members, 6 members into an FE surface. As long as they're in a plane, that will do. So what I can do is I can go and I can say add, and I can choose my first members to bound that up. But I don't really have to do that. I can just come along instead and say auto select, put it in the front view, and then just Windows, that's click, drag, release, and I'm now got my full surface. So that's the surface defined. Very straightforward. If I wanted to take this bit out, notch it out, I could do that just by removing it, but we don't need to worry too much. Now, if we look at this, we have an opening in the middle for a staircase, and it is sitting in space again. As long as its nodes intersect the plane of the FE surface, everything will be fine. So very simply, let's go to openings, and it would be best to do this from viewing the level 1 and say that I want to make that the opening. So any 4 members, any 3 members will define an opening. And now if you move back to main border, you'll see that that is now an opening, and you can add several openings. Edge supports. There are no edge supports. This is supported by those physical columns. But if I wanted to say, well, I've got a wall along here, that's very simple. I just turn around and I say this and this and this and this actually have a y-axis restraint as a restraint, and therefore that will act as a wall. And we will do that. Very, very straightforward. Loading. The self-weight of the slab will be applied, and that will come in a minute when we go to material thickness. But what we need to do is add in our live load. So what I'm going to do is I am going to add in, very simply, a live one of minus 4 kilonewtons. Very straightforward, very easy. And that's over the whole surface. I could also, if I wanted to, put in the basic load instead as being minus 1.5 and then add another 2.5 to the inner surface. So I could go and say add a new, and it's now a patch load. And this is where we now define where the load goes to. So I am going to very simply go back to that view of the first floor. There's my first floor. And if I go back to 3D, it just makes life easier, and a couple of node points. I am now going to define this as being minus 2.5. So I'm going to add this on. And I now define the points it's attached to. And I'm going to say there, to there, to there, to there, and back to there, and apply. So that's now applied that. It won't actually apply to the opening. And close. So yes, I did need to close it. So now what have I got? I've got my gravity drawing all loads. I will see the two different loads on this. I have the inner load and the outer to give us the two. So patch loads are very straightforward, very easy to do. The other types of loads we can handle are very straightforward, and that is, I'm just going to add this in as another load. Very simply, is a line load, and I'm going to make this line load minus 12 kilonewtons, and I'm going to put a wall around it. And in this case, I'm lucky I can just use the same node points again and make that a dead load. So that should come back out 1, 2, 3, 4 as a line load. So a continuous line load. That is a perimeter load, which is for the whole outside of the surface. And if I ask to draw the line load, there we'll see that now applied. So that is now applied as well to the structure. And we don't have to obey loads. We can introduce our own load points. So if I turn off all of these other graphics and add in another load, which is another line load, I'm going to make this be minus 20. And I can put it anywhere on the structure. And sometimes it's easy to come along and just put it, say, from this point over to that point and say apply. And I now have, when I close, my line load drawn across the structure as well as a y-axis line load. So that is how simple it is to apply loading. If I was to come along then to the material thickness, this is where we get into the information about the surface itself. And we use a codified material concrete, and we'll use C3240. And we'll give it a thickness of, say, 250. And that all works very, very well. And that allows us then to have this surface. The final thing, and we will deal with those later, would be attached beams. So if we look at our FE surface, if we look at our loading, our supports, we'll see that we have foundation supports for our columns. We have nothing intermediate, but if we go quickly and analyze static analysis, it's going to do a mesh. And I'm just doing a dead plus live. I will deal with loading cases themselves later. And we will see that it's created itself a very coarse mesh. Now, every single node point that comes down as a node and every single column that comes up from below will have the mesh coming into it. What you don't need to do is you don't need to introduce your columns 100, 200 millimeters in from the edges. You can do that if you so desire, but it's not necessary. If I was to come back out and say modify, so move some columns, and I'm going to take the whole members, and it's this one, and I'm going to say the columns are 200 square. And if I now move those in the z-axis by 100 millimeters, so positive 0.1, and I will preview the changes and say apply, you'll see now we end up with two nodes. We have the external node for the edge of the surface. We actually could get rid of that external node and have the one node just internal on the slab. And that's fine. But if I come back out of that and I look at my mesh again, so analyze static, and reanalyze with the new mesh, we will see automatically that it has identified the nodes close together and it has refined the mesh down automatically for us. Now that's where we start to get into problems, and this is why we don't recommend that you just pull these in, because it's making no difference to the spans really. And you'll see that we can end up with quite obtuse shapes. They're still quadrilaterals and they're still valid, but occasionally with these very close distances together, you can get surface elements that are nearly triangular, which will cause you errors and the like. So we don't recommend that you pull these in unless you have to. So if I just took those all back out again, no, I'll leave them as they are because it'll actually show another thing. What I now want to look at is what we get when we come into the design, into the results. So let's look at our results and our graphical results. And I'm just going to give you the first floor. So we're going to view plant level 1. And obviously we need to go into shell elements. And if I look at something called the maximum errors, we will see that we've got big errors around here. And we've got smaller errors around here. But we can counteract that quite easily. And the errors themselves may look big, but they're not necessarily as big as you think they are. But in this case, I would say that those are considerable in those areas here. So what I would propose to do is to come back and fine-tune this. So back out to full frame. Under analysis, we have a lot of options. The default was 1 meter. So we could reduce that down to 0.5 meter, and that's going to give us 4 times the number of elements and reduce our errors. Or we can keep it coarse, and we can come along and we can say we want local mesh intensities. So I want to reduce the mesh down to 0.2, and I want it to be out to, say, 3 meters. And I can then say, take and apply it to all of these points that were problematic. And even the internals here are worthwhile considering. We could even do those nodal columns coming in from above, but we don't need to. So if we come back out now and reanalyze that, it's going to remesh and reanalyze So now we've got this finer mesh at each of these points. So looking at our level 1 plan, looking at our results, graphical, in the shell elements, we'll see a lot less area that is needing to be resolved. And we can see we probably missed that node. And we're saying that we may want to consider those ones as well. But, it's not the be-all and end-all. Finite Elements does have an inherent amount of error, and this is not the real error. This is just at a very minuscule point. And it's a point that we will actually ignore during the rest of the design. So let's have a look at what else we can look at. We don't want to just look at errors. Membrane stresses? No, we're not interested in those. Axial loads? Yeah, well, no, we're not interested in those. Here we come, MX. So this is the moment along the X, so it's bending, sort of, you think, going hugging, sagging, hugging, sagging, hugging, sagging across that direction. And then we can look at the same MY. But because this is a solid, we want to consider this in more detail. We want to consider the effects of any shear at either end of each of the elements. So that's where we come to using something called MRX and MRY, the wooden armor force values, and they give us more realistic values. Now, that's great. Interesting. But what you'll see when we look at this in 3D is if I go for a color contour, you get these very high peaks, but they're very high peaks over very small areas. So we have a couple of tools that we can work on to minimize that, and one of those is the peak smoothing. So I am going to go ahead. So for that peak smoothing, we can do a couple of things. One of the things we can do is we can say, when we identify these peaks, let us ignore everything to a area around it. So a diameter of 0.2 and apply. And that now reduces everything so that we don't actually consider what's happening inside these areas. We're smoothing it out and ignoring it inside those areas. And that gives us better indication of moments. But we still have these broad, wide values. And one of the ways to get around that is to think about going for strips. So I'm going to introduce a MRX strip, and it's going to be from this node all the way through to this node, and apply. So let's have a look at it in 3D. You'll see this, and you can see the cropping over the peak smoothing, and we will see some values coming across. We're seeing 155 kilonewton meter moment across that 151, 155. But that's only over that tiny width, that 1 millimeter wide strip. 100 mil either side, that will have reduced considerably. So we wouldn't want to design for that moment. So what we do is we introduce an averaging. Now, we normally recommend about 3 to 5 times the thickness of the slab as being a very good average. So I'm going to say it's a 250 slab. I'm going to put it at 1 meter wide. So that's like 4. And apply. And now that's come down to an average value over this width of 128 and an average here of 133. So we could use this set of lines and peak smoothing to get us better results. And likewise, the 24 and the 21 that we have here, if we turn off the peak smoothing and reapply, that's 25 and 22. So it's not quite as bad on the sagging moments. Now, I'm going to step back now and look at another structure because I want to introduce to you another facility that is important in the frame analysis, and that is patterned loading. I have an example here I want to look at. There we go. Somebody had asked about piled foundations. And yes, when you do pile foundations, you just put supports in under the slab where every single pile is going to be. But I would recommend you actually drop little stub columns of the diameter of the pile, because if you put stub columns the diameter of the pile, then you're going to get, if you have the slab design software as well, the punching shear done. Now, if we look at my supports, I put them at the bottom. Some people just put them at the top and let the columns hang down. That's not really a problem from an analysis point of view. But what I want to look at here is if I go to results and graphical results, and I need to reanalyze this. There we go. I've just done the first 6 loaded cases, and I'll explain what they are in a minute. I want to explain the effect that they have on your design, and then we can look at this. So let's just look in top view, and we're just going to window this slab here. That's all I'm interested in. So let's look at the MRX. So what we've got is peaks and then troughs. And I'm going to just put a line across this for you so you can see this in better idea. So I'm going to create a line from here all the way across to here and apply. So if we look at the values, we will see that we're getting 68, 38, 43, 43, 38, 39, and then the 63, the external span. But that is with all spans loaded, and obviously we're missing the peak smoothing parts of our surface. If I was to come and say, well, actually, let's look at alternate spans loaded. I think that's the wrong direction. I think it should be this one. That's better. You'll see now we've got not 68, but 72. Because this is loaded and this is unloaded from live load point of view. And if you then look at the next loading case, it's the opposite. And it's now 57, and that was, I believe, previously 38. So there's a significant increase in the moments when we do sagging, when we do pattern loading. And that's important to understand. Now, that variation isn't as significant if I go to my other slab, because my other slab has a lower live load. So the live load is not as significant. So when you have high live loads, it's very important. So if I go in and create another line load from here to here and apply, you'll see that if I come from dead plus live ultimate, and it is coming in there 32 and 19, when I go to the next case, it's 33 and, well, that's the minimum. That's 24 And then, so 24 from 19 and 33 from 34. So with the lower live load on the structure, it's not as big a percentage change. So how do we do this? That's the very interesting question. And that is all down to two things. Under the loads, when we applied our surface loading, we applied it as live alternate, not live or L1. And this is again live alternate. So that was the first trick. We designated the live loads to be alternate, which means they're controlled by another third party. And if I go to my loads, I will see there's something called alternate load patterns. So I'm saying that these are all the L1s, and these are the L2s, and then the ones I was looking at, the L3s and the L4s. So very simply, I can come in and take in and out groups if I wanted to play fun and games. Take that out, put that in, and then do that. I could do that. So very easily apply pattern loading as groups 1 to 4. What I also then do is under loading cases, very simply, I have loading combinations for D1 and L1, L1 only, L2 only, and then repeat it for the L3 and 4. I like to do all spans loaded on both L1 and 2 and then 3 and 4, just to make sure that nothing's been missed, because the values should be the same. And then in that direction, the patterning of that load. And you can do the same for your serviceability if you want. And that's how we did it. Now, we also did that very quickly through the auto-generate, because I had saved myself a template of files that I was able to import and use over and over and over again. So I have a template of different parameters, including dead and live, wind, and whatever. So all very, very easy to do. Now, we looked at some of the problems. Okay, I'm going to look at a more detailed slab, and I'm going to talk about some of the errors that can occur. So this slab also has pattern loading, by the way. If you look at the pattern loads, and you'll see we have pattern loading. It's interestingly a wee bit squiggly because we have a transfer slab scenario where a column above turns into 2 columns below, or we could have had vice versa to make it even worse. From that point of view, we're not worried about that. I want to look at my results and discuss 1 or 2 problems. What first thing I want to do is to talk about columns. If I was to go to a column and merge columns, now I've moved this column so it's off any grids. So this is sitting in free space. If I merge that, I have no node point there. It's just one member, full stop. It is a single member from top to bottom. If I now go and analyze this, going to remesh it, and I am probably just going to quickly do one loading case just for the brevity of it and analyze that. Here we go, done. Let's look at our results. Graphical results. And one of the ones we haven't looked at prior is the displacement. And we need to look at displacement to understand if a structure is behaving the way we expect it to work. And the first thing we will notice is that it has actually taken this single member and put a node back in at the level of the surface. Now, if we look at the displacements here, you'll see that this is the 0 because it's a wall, it's sitting on a wall, it's not moving down. But that doesn't apply here. It applies to this one, but not to this one. And there's a very good reason for that. And that reason is if I go into members and say create add members, there was no member cutting across. So where we have two surfaces that cross each other, we do need to have a member between the two surfaces defining it. We have that member in this surface, but if I go to this surface, we don't. So what I'm going to do, I can just do it as a quick add member. Doesn't matter what it is. I'm just going to come in here and say, oh, there's my surface. I need a member from there to there. Now if I reanalyze, I will find that I have my support from the wall at that level. It remembers my suspensions, thank goodness. And here we go, back into results, graphical results, elements. And there we can see we're getting that support from both surface edges. So we're getting the support on this surface from this wall. And that's an important thing to remember. But we don't need to define the walls as two separate surfaces. This was actually defined as one surface, and this is another. This is one surface over the full height. All we needed was that member intersection between it. You're coming in at that level. And we can see our transfer slab coming through here, giving us our forces as we expect. So that's a very, very important thing to remember. Now, one of the other areas that we can use to refine our meshes and improve things is when we go to FE surfaces, we can ask it to mesh inside, to members inside FE surfaces. If you think about it, there's a member here just for the pattern loading going from this node to this node, but there's no division of the FE surfaces. Whereas if I take that and say, okay, there should now be these lines to be used as part of the surfaces. If I was to go to here and say remesh, it's now going to include all those surfaces, and it's going to identify the edges of the members and everything as part of that surfacing and work a bit harder to get them all done. And you'll now see when you put it in plan that we do have more realistic. Now, the other thing we want to consider is, or did I click the wrong one there? Yes, actually, I clicked the wrong one. I've done this back to front. I clicked wall column interfaces as part of the mesh distinctions. I wanted this one, and that will give me again, and I can just analyze at this stage. Now the fingers need to be crossed when you do this, to be honest, because you need to be careful that you end up that you get a mesh that works properly. So it's not something I recommend with every single surface, every single structure. So there we go. And you can see now, because I asked it to mesh to internal members, I've got one element here and one element there. And that does give you a more accurate analysis in some respects. Not necessary, but certainly the other meshing to internal columns and walls can be very useful for reducing your errors right down. Now, a couple of little questions I want to look at that have been asked is to do with tweaking models and doing weird things. And the first one is a stepped slab. So I'm going to do a stepped slab for you. So stepped floor, open. We've got a slab, but in fact, if I was to look at this without this, if I was to go into create, because I will be creating in a minute, we will see that we've introduced a line down here because we want to step it so that it comes along and drops down. So what I'm going to do, first of all, is I am going to copy some members. I'm going to take this one, and this one, and I'm going to shift them down once. I'm going to add wee connecting members. This is a little tip for you. And I'm going to move it down by 0.5, just so we can see. And I'm going to preview that. And now we've got this, and it's minus 0.5 because we're going down, Tommy. And there we go, apply. So what I'm now going to do is going to take everything in this side down. So modify, move. And I am going to take whole members. And actually I'm going to do ends. So I'm going to put it in front view first. All of those. And then I'm going to take that end. That'll be good. And that end. And I'm going to move them all down. So I'm going to move them from this point down to that point and preview. Looks good. Apply. So now I've got a step in my slab. Doesn't have to be the overall depth. I've just accentuated it so we can see it. It could be 100 mil. It could be 200 mil on a 300 mil thick slab. That's not a problem. What we need to do now is to look at our FE surfaces. And anything in here will get us there. So our surface has now got annoyed because it's disconnected. So let us go to this first surface and take these members out and apply it to that member. So that's that surface done. Let us add in a second surface. So add, auto detect. We're going to have that, and that. And the material should come through the same. It's remembered it. And the loading, it won't remember. I'm going to add in the same load. I can't remember if I think it was 4 kilonewton live. And I'm going to say minus 4. And then I just need to create 3 little surfaces for the step itself. So add in a surface. Sorry. And in apply mode. There we go. So add a surface and in apply mode. There we go. And add a surface in apply mode. There they go. So each surface is rigidly connected to the other surface unless you tell otherwise. So we're going to get our full homogeneous connection between these. We go out and analyze this, very straightforward. Analyze static analysis. Going to remesh, space frame. So it just meshed the one element on the vertical. Maybe we should consider that to be a wee bit more than that, so that we get this a bit more detailed. So possibly come along to FE surfaces, local meshing. So I can turn around and say, well, actually, I want this mesh to be 0.25, and then come to the next one and make that 0.25, and then the next one and make that 0.25. So having done that, if we remesh, you'll see it's giving us a finer mesh along that interface. Analyze, very straightforward. Static, sorry about that. And we will see that we now have the graphical analysis and bending moments. Sorry, no. Bending moments. And you'll see what's here carries forward and what was here carries forward. So basically, although if you were using our slab design program, you wouldn't be able to design the wall, whatever the moment here is carries through the steel down and then across, unless you're in a very, very deep wall. So it's not that big of a problem. And that's MX. If you go to MRX, that's more realistic. And there you go. And we can see that coming through and that just going through. And that's how simple it is to do a stepped surface. Now, the other question I have frequently asked is about walls and how do we get the axial loads on walls. Well, there's a couple of things we can do. First of all, I'm going to create another surface. So I'm going to right mouse click and I'm going to add a dummy member from here to here. And now I'm going to say that this surface is going to be, sorry, apply mode. There you go. So thickness, we'll leave it at 200. Supports, this is going to be continuous between this homogeneous, but we're going to make the base. So we're going to apply a fixity to the base. That's going to be a y-axis only, so no moment at the base, but you're going to have a continuous support there. And that's all very, very simple. So analyze that. FE surface, static, off you go. Remesh, reanalyze, and you'll see your surface here. And you go into your results and into your graphical results. And here we go. So what we can do very easily is to put a line between here and here. Now, we need to be looking in the right direction, so if we look at that, we will get a little contour diagram. If we choose our axes correctly, and we need to see what the axis is, we'll see it's the Y that we're after, not the X. So let's go to FY, and we also need to be seeing the direction of force. So local is going to give it to us in a weird axis. What we would prefer to see is in the local Y. And that can be fine-tuned to see what our actual values are. So if we show values, we'll see we go from 150 down to 44 as our intensity, and naturally we can get more accurate values if we just quickly come back in to local mesh intensity and choose this mesh. So that's the nodes incorrectly chosen there. Local surface mesh options. Choose this surface and let's take this mesh down to 0.25. And close that. So if we now go and ask it to remesh, we'll find a finer mesh here back into results, which will ask for an analysis. Won't affect the bending in our slabs or anything like that. And when we come down to our line here, we'll be able to see the slightly more accurate set of results. Now there will be some spikes due to the localization of the mesh, but you can take the values through from the basic values as a indication of your pressure. Just see if I can get some more values. Certainly 43 is coming in as a drop there, and then there's slight inaccuracy as you get to the very edge. So you're looking at going from 43 up to about 150. And I should be able to change the interval here to get some more accurate values. And there we go, there's our bearing coming through. So that's around 150 down to 45. So an average of 100, 150 to 50 would be your bearing pressure, your load per meter run on this. But naturally it's all going to be on this end because of this having the load coming through from here. Last thing I want to look at is rafts, and then I'm going to look at some of your questions. And I get nervous when people say rafts. There's a couple of reasons for that. Right. Raft subgrade modulus. This is very enlightening, is all I'm going to say. For rafts, there are like little garages, something like that. Wall loads around the edges, a couple of point loads from a lintel. All identical, nothing too scary. Even if one side is slightly different from the other side, but that doesn't matter. Each one is identical. Same density of mesh, and reassuring that it creates the same adaptive mesh. What's different is the support conditions. So when you're doing a raft, you use something called the subgrade modulus. So here we have a value of 10,000. Here we have 20,000. Here we have 30,000. You can see where this is going. And here you have 40,000. So let's go and analyze. Static analysis. So because it's subgrade modulus, because it's spring supports, it's doing a slightly longer analysis because it's an iterative process. So results, graphical results. We could even just look at the deflected diagrams and we'll see that this one goes down more than this one, as you would expect, because this is a quarter of the stiffness of this one in the soil. But if we go to the shell elements and we look at in plan how it applies. I'm just going to move this up out of the way. The MRX, so we're spanning that direction. You will see with a very small subgrade, we're actually taking a lot more here. Whereas if we go for a very stiff subgrade, it's acting like little cantilevers nearly. And it's so stiff, it's all in here and it's nothing to do with this. So if we look at the wooden armor in the other axes, again, we have it bidirectional, spanning that way and that way. In here, we have a lot less spanning this direction because it's stiff. Which one you choose is a very, very good question. It's up to you inherently. But if I look at my little notes, I have a document here that I find online. I'll give you a link to it that gives you typical values of subgrade modulus. So clay can be from 100,000 all the way down to 10,000. I find this a more applicable set of values. So for a bearing capacity of 200, you'd be dealing with around 18,000. And for something very high bearing, you'd be dealing with up to 50,000. If you're in the sands, again, massive variation in the stiffness that you can obtain. So it's really a question of deciding from your site investigation what you want to use for your subgrade modulus. But it's very significant. What you choose will reflect the results considerably. And that is worth noting. Now, I've done slabs, I've done very straightforward things. What I want to do, and this time I'm going to open it from here, which hopefully will be a lot quicker. But what I want to look at is what we can do. We can do the step floors, we can do the transfer slabs, we can do culverts. So we could do a box culvert for surfaces, and we could put triangular as well as uniform loads onto that. We can do our spiral type staircases in stainless steel. We can do a basement with walls and footings and everything in an upper slab. We can even do our houses. And I'm wanting to look at this culvert and just open it up. Let's look back at the loading and how we do these unusual loads. So it is just a box. Let's look at the loads, the FE surface loading. What I'm dealing with here is an area load over the full area, but I've told that it's varying. So it's a tick for varying load, and then I've told it 3 values. And it's a varying load. So a couple of things we need to tell it is 3 points give us any surface. So these 3 points are 5 kilonewtons at 4, 5 kilonewtons at 8, and then down at 6 we have 35. So a 30 increase. So any 3 points give us a load on a surface. Very straightforward. So instead of being uniform, it is varying. So I can say it is, it'll be 5, 5, what the heck's happened there? I'll explain in a minute. Well, what's happened is one's positive, the other's negative. So I just need to make them both go in the same direction. And that's how simple it is to define a triangular load onto some sort of culvert. Now, in this instance, we don't have any supports other than the subgrade modulus. So what we have is we've got little static supports stop it just sliding all over the place. So we have just given X and Z displacement supports, but no Y-axis support. And if I go to nodal supports, we will see that these are on those two directions. Now you could get pedantic and say, well, actually you only need it at two separate points, and you probably don't need that in both cases, and that's going to give you the stability you want. So that's how you do need at least one support in each of those two directions. That gives you a couple of resistance to prevent your structure just moving along the page out of the way. Somebody's wanting to see this spiral staircase example. It's nothing special. It's just a whole lot of surfaces. How do you take account of soft spots in surfaces? Well, if you're going to start introducing soft spots, you're going to have to start cutting your FE surfaces up into separate subsurfaces and then change the subgrade modulus under one or two of those. So spiral staircase, open. So that's how you would do that. You would have to just go into that. Or what you could do is you could try and do an additional reactive load in either direction on a small area. So all this is a whole stack of surfaces, and just so that it looked pretty, I put the risers and the treads in at slightly different thicknesses so you could see them, and I put the walls in at two different thicknesses so you could see that it was facets. But each one is its own facet. We are just here dealing with nodal points that all match up and work together on a curve. So you can bring that in from AutoCAD or the likes and start building it up quite easily, or use our position on arc and position on circle tools to do the same. Now, I don't want to get into too much detail in the slab design program, but I do want to show it to you, because rather than going through just doing the boring stuff, we're going to take, actually, we'll take this one we were dealing with earlier. And you saw how we could do strips for our moments. We can also do strips the same way for our areas of reinforcement. So under this shell elements, and if I had line elements, yeah, there we go. So they were on the first floor, and put those there. We can change those from being MX to being area steel top or area steel bottom. So we can specify our design code, our yield stress, our concrete grade, and we will then get the areas of reinforcement that we require in the design. And that's for that little strip. And that's, at the minute, it's without averaging. If I suddenly look at that and look at some of those horrendous values, 740 coming in there, if I was to apply a 1 meter strip averaging to that, the 740 comes down to 530. So still a bit more than 393 mesh or whatever, but we can do that basic design there. What we can also do, and I'm just not going to go in and do it in great detail, is we can do proper slab design if we have the second module for slab design. So here we go. And what we've got here is a couple of the slabs. We've got a slab here, and we've told it that our default is going to be cover, same as previous, rebars 10s at 200. And when we auto design, we will not use anything but, I think, at 200 and 400 spacing. And then just copy that down and save that. So what we can then come along, we see these all fail, is we can then come along and putting it in the plan, what are we failing on? Well, we need to find out what we're failing on. Let's find out. And we're looking at, say, top steel hugging. we can see we're failing. And what we've done using the slab design is say, well, everything works except for these areas. We're going to strengthen those up. So I can take any one of these areas and I can increase them. So I haven't done anything here. So I can introduce a peak there. So I'm going to, so that was basic and it's the peak I'm dealing with. Sorry about that. Add in here. So I've now got an additional set of reinforcement. Now it's giving us a few warnings because it's too wide to be averaged over the full width. We're going to do a more sensible averaging over 5 effective depths. We're still overstressed, so what we do need to think about is these top steel bars, the additional ones. Will we make those 12s or 16s? So it's now okay in that direction. But if you examine, we're probably just needing to make that ever so slightly bigger. It's so short you might not bother. 100 mil extra is only 1 bar, and it's, you know, they'll have a bar out to the edge anyway. And then we want to consider the same in the YY. I'm going to see in the YY, we probably need to come along here and put in bars at 16s. Now we can ask it to actually go ahead and actually size that for us, auto design the selected, and it will give us that same answer, 16s top in this area, and it will have changed the size of the foundation. So we can very easily do a very detailed design. Now, I'm not going to go into this in detail here because there's a separate webinar just on the concrete slab design program. Now, the concrete slab program also includes cracked section analysis for detailed deflections of concrete slabs. And that's also very, very good. We will put links to both the concrete slab design webinar and the advanced deflection analysis and calculation webinar for you. So before I let you all run away, any more questions needed answering? Piles I've dealt with. Columns are at the edge of a slab. Does punching shear take account of the full width of the column? It will take account of most things. If I go to punching and I look at, say, this one here, it's assuming it's a halfway, and most of the time it will show up to be fine. You know, if it's that little extra bit that's going to make it work, you're running pretty close to the wind. But certainly we are looking at allowing the program to include that overall area, even though it's analytically at the edge. Best way to model an opening close to the edge of a slab? First answer might be don't. The second answer is obviously you're going to have to model it using 3, 4, 5, whatever number of members. And you would be highly recommended to put in either a drop beam around that edge or at least mesh down to no more than a half that width. So if the opening starts 200 mil in, you're going to have to mesh to 100 mil either side of that opening is one I would recommend. So what I'm going to do is I'm going to come out of this slab design, and I'm not going to change anything, and I'm going to introduce an opening for you close to the edge and then talk about that. So let's go in and we're going to create a member. So I'm going to take the roof And I'm going to create a slab here. So what I'm going to do is I'm going to take an opening and I'm going to start at, say, 2 meters in. And I'm going to say that the slab is 200, and then the opening is 400. And then I'm going to come along a meter. And then I'm going to come back a meter and back in there. Now, I don't need that point, but in this case, it's probably better to have those points so that, first of all, we can put the opening in easily, but secondly, we can mesh around that a bit better. And there's several ways to do that. So, properties into something in the FE surface. We'll take this surface and we'll apply an opening to here, and there we go. When we go back to the materials, you'll see it's now an opening. So we would just want to have a higher density mesh around that point, and that's no different to what we did previously using this local mesh intensity. I would personally come along and say take all 6 of those nodes, sorry, in apply mode, all 6 of those nodes and mesh them out to 0.1 for maybe 2 meters. And that's going to get you a far finer mesh. But the other thing I was talking about here is beams, drop beams. Now, if I am coming into the, I'm applying drop beams, come back out to full frame here. And I forgot to turn off my patches. Not to worry. So I'm going to put in some drop beams. So if you think, first of all, the mesh was, I think, 300. So let's see what the properties of this slab is. Material surface properties. Let's find out this surface here. What are you? You're 250 deep slab. Remember that. 250. So and I want to put some beams in around here that are drop beams, or maybe even around the whole length here. So I'm going to go to properties, and I'm going to go to member properties and take these members. At the minute, it doesn't matter what they are, they're just converted to an FE slab. I'm going to say, no, this is a concrete member. I have a 250 slab and I want a 250 drop. So 500 overall. So I'm going to go for a rectangle and I'm going to make it 250. And I'm going to make its overall depth 250. That is the bit additional to the slab. And I'm then going to copy that to these. Obviously, that might not be sensible if that's only 200 wide, but it'll be assumed to be in and out anyway, so it's not going to affect analysis that much. Now, as it stands, that has no effect on the slab because the slab itself does not know about it. So if I go to properties and ask for attached beams, I'm going to say now that I want to have these as attached beams, and I want them. Now, the default is going to be centered. I'm going to push them to the bottom, which is more sensible. And I'm going to combine them and use everything. So I'm going to use T-stubs in my concrete design. So having done that, what have I now got is no attached beams. Did I say below? Let me see. Loads, properties, attached beams. Oh, there, they come back out now. They're in now. It just hadn't updated the graphics. So there we go. We now have our little concrete beams attached. And for some weird reason, I seem to have this one the different size to the others. I think I was playing around with something, and that's probably taking the steel. Let me see. Properties. And that is concrete. Yeah, that seemed to have this missed a part. That's better. So now they will all be the correct attached beams at the correct time. When I go into design, analyze and design, they will be now considered to be attached to the structure and be perfectly valid. So let's mesh this out. Just going to go off and do the design. So this is all straightforward. It's just all baby steps. I'm just looking, there don't appear to be any other questions. When I look at my results, graphical, if I turn off the 3D and you do bending moments, so they're all part of that, but this will have the attached beams on it for you. So ladies and gentlemen, I'd like to thank you very, very much for coming along. Any questions, pop them to us at help@masterseries.com. We'll answer it for you. Somebody was asking why the course mesh and why not start one. Well, it does drastically increase the amount of time to analyze and doesn't necessarily give you a more accurate analysis. It's better just to refine the areas that you need to refine than everything. It does really help with the analysis time. Naturally, with some of the big computers, you can certainly go and do all that meshing inside columns and walls and the likes if you are finding your errors are coming out too big. But normally people don't get that worked up about those as long as they're within reason. So ladies, gentlemen, everybody, I'd like to thank you for joining me today.